Hi, everybody. Welcome to Talk Math with Your Friends. I'm so excited. Today's Thursday, and we get to do this again. I'm also really excited to introduce our speaker today. So our speaker today is Dr. Marissa Loving. And Marissa right now is an NSF postdoc at Georgia Tech. And she's going to tell us about surfaces, big ones and small ones, and we'll enjoy. All right, Marissa.
Thank you so much.
And we're recording.
Oh, yes. We're recording this for YouTube, so it'll be uploaded later on.
So thank you so much for that introduction, Kate, and thank you to all the organizers for organizing this and giving me the opportunity to speak, and for so many people for being here. So as Kate said, today I'm going to tell you a bit about surfaces. The goal of this talk is to be accessible to a wide audience, so hopefully I'm not assuming too much background, but I'm coming from the viewpoint of a geometric group theorist, and so I will be kind of looking at a surface through the lens of a group called the mapping class group, which I'll introduce a bit later. So to get started, I'm going to start with small surfaces. Some of my colleagues have been slightly peeved by my choice of calling things big and small, because it makes it seem like these surfaces I'm going to introduce now are maybe not as important as they really are. But as you'll see, there's many reasons to enjoy studying both small surfaces and big surfaces. So what is a surface? When I talk about a surface, I'm talking about a two-dimensional manifold. So this is just something that locally looks like the Euclidean plane. So a very familiar like two-dimensional manifold that we're all familiar with would just be a sphere, right? Just the outside of a ball. And so you can see that it's locally Euclidean by just, if you take a small neighborhood, you take every point, there's a little neighborhood, that looks just like a flat piece in the plane, right? So this is kind of how we experience our day-to-day life. We live on the surface of a sphere, but we feel like we're living in a flat space. At least I certainly did while I was a grad student in Illinois. But yeah, so this is one example of a surface. Another example of a surface is something called a torus. And this is something that we could all construct very easily just in our hands if we had really flexible pieces of paper. Because the way you do this is you take a square or a piece of paper and you identify the opposite sides. And so you first roll it up to get like a cylinder, and then glue the ends of those cylinders together and you get something called a torus. This is also called a genus 1 surface because it has that one kind of distinct hole in the middle. Okay, so this is an example of a surface. And so a very basic question that we can ask about surfaces, this is the kind of question us mathematicians like to ask a lot, right, is when are two things the same? So any type of object that you study, you want to have some sort of classification, some way to tell them apart or see that they're the same thing. Okay, so sometimes this feels like a very easy question to answer, right? So here's three surfaces that we've seen already two of them. So there's the sphere, the genus 1 surface, the torus, and then the genus 2 surface. And I could ask you if you think these surfaces are the same, and probably all of us have a sort of gut feeling that these are not the same surfaces because they have this kind of distinguishing feature of not having the same amount of holes. But you could say maybe there's a way for you to get from one surface to the other. For example, what if you took this sphere and kind of just like punched down through the middle and pinched it together and created a hole in the middle, and then you have the torus. That would be some way to transform something like a sphere into something like a torus, but these aren't the sort of transformations that we want to think about. When I want to say that some things are the same, I want to say it up to something called homeomorphism, which is somehow something very smooth and continuous, so I don't want to tear or destroy my surface or do anything violent to it. So this is the type of equivalence that I'm going to be talking about. Okay, so these are some examples of surfaces that we might intuitively think are different. But what about these three surfaces? So these are surfaces which still seem like they have some things in common, but we have some things that look kind of distinct about them. For example, in the top right-hand corner, that green surface, it has this kind of spherical component, whereas like this orange one kind of looks like a fidget spinner. It looks somehow much flatter and smoother. And so we want to know if these things are the same. And so this brings us, this is already what we're doing when we just have surfaces with like this genus component, right? But we could make things more complicated. For example, that very first slide, my title slide, this is a picture of a urchin shell, like when you know those spiky little urchin fauna. If you have it, like take off all that spiky stuff, you have this really pretty shell underneath. So this is a picture I took at home. This is an example of a sphere where we took out some points. So I call those punctures. So this is an example of like a 6 punctured sphere. And so this is somehow now we're adding a little more complexity to our surface. And we could do this in another way. We could also add boundary components. So instead of just removing a single point, maybe we remove an open disk. And so we have these kind of now, these circle boundary components. So now here's a little bit more complicated. We have surfaces with genus, we have these punctures, we have these boundary components. Well, it turns out these kinds of different, I guess, descriptors, these adjectives I've assigned to our surfaces, these are really all that can happen. So this brings us to the classification of surfaces. And it says if that we have a connected orientable surface, then it's determined up to homeomorphism by the number of punctures, the number of boundary components, and its genus. So this is great, right? Now we have these kind of 3 numbers, which are telling us the homeomorphism type of our surface. And so when I say finite type, I think I say finite type. You folks are covering my slides a little, but I think I say in there finite type. What I mean by that is that when I have these 3 numbers, the genus, the number of punctures, and the number of boundary components, I want those all to be finite numbers. So I want the fundamental group of my surface to be finitely generated. And then these other first 2 words I use here, connected and orientable, in case you're not familiar. So the reason that I want to talk about it being connected, so I want my surface to be a single piece. I don't want to allow there to be 2 pieces that I kind of put together in a box and say, oh, this is one surface. Because if I did that, then I'd have this kind of issue, where on the top, I have these 2 surfaces, which if I said, oh, let me just call that one surface, has genus 3, and then on the bottom, I have this single genus 3 surface, well, I wouldn't be able to tell them apart. So I want to really enforce that we just look at single connected pieces. And then the other thing that I ask is for it to be orientable. And so for the rest of the talk, I'm always going to be talking about orientable surfaces. And what this means is that I want my surface to have 2 sides. I want it to be able to paint one side one color and the other side another color. And so what this is really ruling out is things like this picture here, which is called a Mobius strip. So one way that you could actually build your own Mobius strip is if you just take a piece of paper and instead of gluing the sides directly, like I did when I built the torus, you flip one over and then glue it. And so this gives you something that you can actually only color with one color because it's just a one-sided thing. And so I'm going to rule those out my surfaces too. Non-orientable surfaces are very interesting and there's lots to study, but it's not the kind of thing I think about.
I have a question, Marissa.
Yeah.
A couple of us are surprised that punctures and boundaries are handled separately.
Yes. Oh, so that's a great point. So they're handled separately, but somehow they seem very similar. And so one of the reasons that we handle them separately is because later on when I introduce something called the mapping class group, and I consider maps of my surface, how they act on a puncture versus how they act on boundary is a little different. So typically when I have boundary, I want that boundary to be fixed point-wise, and I don't want to allow my homeomorphism to exchange different boundary components. Whereas when I just remove punctures, I'm going to allow my homeomorphisms to kind of shuffle those punctures around and permute those punctures. So that's kind of the reason that we differentiate between them.
Awesome, thanks.
Okay, so let's see, what's next? Okay, yeah, so we can come back now to our same picture. And now that we know this classification, well, we can determine that, for example, this orange and this green one, even though they have, in some sense, they look a little like they have different geometry, the intrinsic topology of the surface is the same because they both have genus 3. And it turns out actually that that red and blue surface in the bottom right-hand corner, that's also a genus 3 surface. It's a little hard to tell because it almost looks like it has 4 holes. But if you take those front 2 and you kind of lay them out flat so that it's laying flat just like that fidget spinner one, then it actually has 3 genus. And so these are actually all the same surface. Okay. So next, I kind of already hinted at this a couple of times at this point. So as I said, I'm a geometric group theorist, and so I like to study topological and geometric questions using groups, and my favorite group is the mapping class group because it kind of captures some of the intrinsic nature of a surface. So what is the mapping class group? One way to think about it is that it's the collection of symmetries of the surface. So symmetries often we think of, for example, if you think of the dihedral group, you can think of that as symmetries of the square. So you act on a square by rotating it, by reflecting it, and then you look at all the compositions of those actions. And this is kind of a similar type of thing, except now that we have a much more complicated object, our symmetries are going to be more complicated. So a somewhat more formal definition of the mapping class group, which I'm going to denote by this map S, is it's going to be the group of orientation preserving homeomorphisms of my surface up to homotopy. So when I say homeomorphism, again, this is some sort of like continuous map on my surface. And up to homotopy just again means I'm gonna kind of go up to this equivalence where if I can kind of squish and deform my maps to look the same, then I'm just gonna say they are the same. Okay, so let's look at some examples of what these homeomorphisms are, or these mapping classes, these equivalence classes of homeomorphisms. So one, straightforward symmetry, this is a very nice type of symmetry that we talk about for lots of objects, is doing some type of rotation. So for example, for this genus 3 surface, if I arrange it very symmetrically like this, I can think of an example of a homeomorphism would be a rotation by 2 pi over 3, right? Where I just click each of the genus holds over back onto the next one. And you can see I marked these blue curves. You can see how those blue curves as a collection are kind of preserved by this rotation. They each kind of get mapped to the next one, but they all get preserved as a set under the action of my rotation. Another type of homeomorphism that's a little bit more complicated, but is like kind of a building block for all the types of homeomorphisms that we can think about, is called a Dane twist. So this type of twisting is we can take a curve like this red curve, which I labeled alpha over here on the left, and we can do a twist about it. And so one way to think of what this twisting is to think if you cut open along alpha, and now you cut open your surface, you have your two circular kind of like annular neighborhoods, and you're going to twist one around by 360 degrees and glue it back together. So if you did that, you get, again, a genus 2 surface, right? It doesn't really look like anything's different, but the way you can see kind of the action of how this is acting on the surface is by looking at what it's doing to another curve. Here I drew this curve beta in blue, and see how that twist around alpha affects what beta looks like. And so you can see now, instead of just intersecting, going kind of straight around that genus, our curve beta under the image of this twist kind of goes all the way around alpha and then goes back to its original path. And so these types of twisting homeomorphism, these Dane twists, are going to be really important to build up more complicated maps on our surface. Okay, so for example, you could do a ton of twisting. So here I've drawn a whole collection of curves on my surface, and I've shaded them in different colors. So I have some of them are red and some of them are blue. And one example of a homeomorphism, which I can't really show what it does, but I can describe how you get that action, is if you take all of your red curves and you twist all of them to the right, and you take all your blue curves and you twist all of them to your left. And because we kind of have our curves spread out all over our surface, this twisting is going to somehow mix up our entire surface. And so this is sort of a more dynamically complicated homeomorphism of our surface, but still coming from these just really simple Dane twists that we introduced. Okay, so what is all of this leading to? Well, this is leading to one of the most fundamental results in my area, which is called the Nielsen-Thurston classification of the mapping class group. So the classification is basically this partition that I've drawn here, where we have, I kind of gave an example of each of these different kinds. We've already seen some of them. So over here on the left, we have an example of a finite order homeomorphism. So here it looks like I just have like, I think that's a 10-sided or something polygon. And so that, if you glue up according to the colors, is actually going to give you a genus 2 surface. And so one way to realize what this map on my surface is by cutting it along those curves, and then just by doing a rotation of 2 pi over 10, right? So we can do this rotation. This is finite order, because if we do that rotation 10 times, we get back to where we started. So we get back to the identity. And this is an example of a finite order one where we don't fix any of the curves on our surface. While we do that permuting, until we get back to doing it 10 times, every curve on our surface is getting permuted around. Whereas that other rotation, which we introduced a few slides ago, where we took our genus 3 surface and we rotated it by 2 pi over 3, we already saw there that not everything was getting permuted, because those blue curves we drew, those were all getting preserved under our rotation. So this is an example of something where we are finite order, but we have some extra structure happening. And this extra structure is something called being reducible. So this is what our Dane twisted is an example of. If you're reducible, you're fixing an entire collection of curves on your surface. So when we did the Dane twist, for example, we did that twist about alpha, we actually fixed that red curve, right? We cut open along it, we twist it around and it came back to itself. Alpha didn't change. And so this is what we call a reducible mapping class when we fix a collection of curves. And then on the big outside, that pink region, I have something that I've called pseudo-Nassov. And the definition for a pseudo-Nassov is a little bit more complicated because it involves its action on this other underlying structure on our surface. But one way, because of this classification, that we can characterize it is by saying that our pseudo-Nassovs are our infinite order and irreducible irreducible mapping classes. And so one nice characteristic of a pseudo-Nassov, for example, is that they don't fix any curves on our surface. So you can see how you get some sort of very, very dynamically interesting things happening, because you could kind of look at the forward iteration of a curve on your surface, and you're going to get some behavior that's continuing. You never come back to where you started. And so one example, I already talked through this a little, so I'll go through these slides quickly, is we already saw this finite order example of the rotation. We saw the reducible ones where we're twisting along our curve alpha and fixing that curve. So we have alpha as our reducing curve. And then that last picture that I showed, this is actually an example of a pseudo-Nassov. So this is something that is mixing our surface, and it's actually preserving some underlying flat structure. And so this is coming from another construction of Thurston, which we don't have time to talk about. But just suffice it to say, like, we've already seen now a way of taking these kind of very simple things called twists and building up something that's very interesting and has like a lot of things going on. Okay. So let's get back to the basics. We've kind of gone off into like thinking about this kind of very important, very big fundamental classification theorem, which is great. But we could ask some much more basic questions, right? Like, there are much more basic questions we could ask about our group. And here's just a handful of them. For example, is it finitely generated? So to a group theorist, being finitely generated is really great because it allows you to turn a lot of problems about your group into something that's very combinatorial or algorithmic. So this is a nice thing to know about your group. You could also ask about its center. So the center of a group, right, is the collection of elements in your group which commute with every other element in your group. So for example, when you have an abelian group, like if you have Z, then every element in your group commutes with every other element. So you have a huge center. Whereas if you have something like a free group, then nothing in your group is commuting with any other elements except the identity. So this is somehow telling you something about this very fundamental property of a group, like kind of, in some sense, how abelian it is. That's a little bit of a simplification, but that's one way to think about it. And then this last question is a little vague, but it's a good type of question. You want to know about structure, right? We're always looking for structure. And so you can ask, are there any things that, Brian, I saw you. Is that a question? Or
No.
You just like structure?
Yes.
Okay, great. Good. I like structure too. So you can ask, for example, are there any unifying structures that its subgroups have? Any sort of properties they all share, or some list of properties that they all have to fit into one or the other? You can ask those sorts of things. Okay. So it turns out that we have a very nice fact about the mapping class group. So this is a classical theorem at this point of Dane and Licorice. And it says that if we have a surface of genus at least one, the mapping class group is finitely generated by Dane twists about non-separating simple closed curves. So this is wonderful. And it turns out that it's not only finitely generated, but you can write down like a very nice topologically simple generating set. So for example, here's one such set. So this is called the Humphreys generators for the mapping class group of a closed surface. And so this picture is describing the generating set. If you take a Dane twist about each of the curves I've drawn, this gives you a generating set for the mapping class group. And so this is like so very nice because we have now like such a hands-on picture of like what every element in the mapping class group can be derived from, right? Okay, awesome. So yes, it is finitely generated, and we know what it's finitely generated by. Okay, so what about its center? So it turns out that the mapping class group has trivial center. So it's really not abelian. And we'll talk more through the proof later. It's actually a quite easy proof. We just have to kind of introduce one trick first, and so we'll talk about that a little bit later. And then we're kind of down to this somewhat nebulous question about this unifying structure. So I gave this question because I have something in particular in mind. For the mapping class group, we have something called the Titz alternative. So this is a theorem of Ivanov and McCarthy. And it tells us that the mapping class group satisfies something called the strong TIS alternative. And that means that every subgroup is either virtually abelian or it contains a non-abelian free group. So this is very nice. This is something that kind of comes from the angle of studying the mapping class group as somehow being a group that we'd like to be linear, even though we don't know if it is or not. A lot of the things that you study about the mapping class group are doing them in kind of analogy for the things we know for linear groups. And so this is like a really nice, very strong subgroup alternative that the mapping class group satisfies. So what does it mean to be virtually abelian? It just means that every subgroup is either, so I said virtually abelian or contains a non-abelian free group. So either it contains a finite index abelian subgroup, so somehow a very large abelian subgroup in it, or it contains a free group that's not Z. So that's what I mean by non-abelian free group. Okay. That was a little bit of a mouthful, so if anyone has like questions, feel free.
So geometrically, is that kind of like you have to have these generators and either they're free and they don't interact at all, or they are sort of totally separate from each other and they are abelian?
Yeah, so this is a good way to think about it. So in the mapping class group, right, that is like the whole story, right? We're looking for either free things or abelian things. And you can think of it in terms of like two generator subgroups. And so really what it's saying is like if you have two things, either they live on disjoint subsurfaces where you get that abelianness, or they're actually pseudo-Nausov on the same subsurface. And so they heavily, heavily interact with each other. And so that's when you get this freeness. So yeah, that's perfect. That's a very like geometric way to think about it. Okay. So it's time to do big surfaces. So big surfaces are awesome. We're gonna basically take the first step where now instead of imposing that all of these kind of descriptors that we talked about before, the genus, the number of punctures, the boundary components have to be finite, we're gonna say, forget about it. Let them be as many as you want. For one, just to make it a little simpler, I'm not gonna actually consider boundary components for these infinite type surfaces. I'll only consider ones with genus and with punctures. And so I want to just get started by looking at some examples of what these can look like. So I have just some pictures. This first set of pictures is from like this awesome paper of Matt Durham, Federico Finoni, and Nick Vlamis, where they study the action of big mapping class groups on complexes coming from curves on your surface. And so these are actually such well-studied big surfaces that they have names. So the one on the left, this kind of elongated one, is called the spotted Loch Ness monster. And you could think of it, I should have drawn it a little bit more descriptively, because if you think of those genus as kind of like each of them bumping up, you can kind of see how it can look like a Loch Ness monster. And then you have your spots, which are your isolated punctures running out to infinity. And then on the right, we have this kind of three-ended surface with genus running out to each end that we call the tripod. Very descriptive, because it has these three pieces. And then you could kind of extend this, right? Why do we now have three ends running out? You don't. You could have, here's another picture that they have in their paper. This has 5 ends that are accumulated by genus. Here's some even more wild ones. So this is coming from this really great paper on the Alexander method for infinite type surface, which we'll actually talk about a bit later. So this is a paper of Jesus Hernandez, Israel Morales, and Ferran Valdez. And here they're building like this, a very specific curve system, I guess, on their surface. And so here on the left, they have a surface which has finite genus actually. But then as you kind of go off, you have infinite amount of punctures because you're doing an infinite amount of branching. So actually you end up with a whole Cantor set of punctures. And then on the right, we get something that has both infinite punctures and infinite genus. Okay. So this is another fun one because it's one that's well studied enough that it has a name. So this is coming from a paper of Juliette Bavard and Alden Walker called Two Simultaneous Actions of Big Mapping Class Groups. And so this is also a paper studying the action of the mapping class group on some complex of curves or arcs or loops. And so this is called a blooming Cantor tree because this has a whole Cantor set worth of punctures, but it also has an infinite amount of genus. So you can think of it as kind of this branching Cantor set with genus placed at each branching point. Okay. So this is some more pictures. The one on the top, this is our honest to goodness Loch Ness Monster. The one on the bottom is often called like Jacob's ladder or just like an infinite ladder. Oh, the next slide is the good one. I feel like I should introduce it. So that now we're ready to actually give what our classification is. So we're very lucky that even in this like wild world of infinite type surfaces where there's so much more that is allowed to happen and so much more varied behavior, we still have a classification theorem. And so this theorem is due to Carrick, Darto, and Richards. And it says that a surface of infinite type, so again, I'm looking at orientable surfaces, is determined up to homeomorphism by its genus, its space of ends, and the subspace of ends which are accumulated by genus. So I kind of, in the previous pictures, I was talking about ends, but I haven't defined what I mean by them. And I'm not going to because it's a little bit complicated. But I will give what I hope is an illustrative example. So we can think of ends of different kinds of groups. For example, if we think about R2 or the real line, we can try to think about what their ends are. And so when I think about ends, I think about it as like ways to go to infinity. And so, for example, in R, we already kind of have a natural sense of the number line. We can kind of go to negative infinity, or we can go to positive infinity. And the way that you can kind of make this a little more precise is to think about what happens as you delete sets, like connected sets out of the real line. No matter how large of a connected set you delete out of the real line, you're always going to get those two pieces on either end. Whereas if you think about like the real plane, right, the Euclidean plane, here, in some sense, it feels like you have more ways to go to infinity, right? You have so many directions to go in. But then when you think about it in terms of kind of deleting larger and larger pieces from, like, if you think of taking balls around the origin, no matter how big of a ball you delete, you're still going to have that connected piece around the end. And so, in fact, it turns out that we have just a single end for, like, the Euclidean plane, but two ends for the real line. And so this is kind of the way that I want you folks to think about it when I'm talking about ends. It's kind of these kind of ways of getting to infinity. Okay. So this brings us to one of my favorite slides, which is to try to actually think about this in terms of now our big surfaces, to think about how this classification theorem is actually letting us say something about our infinite type surfaces. So I have 4 surfaces here, and you've seen 2 of them already, right? You've seen the tripod surface, and you've seen the Loch Ness Monster. And so the question is, are any of these surfaces the same? This is for audience participation.
Well, the tripod has that little part right in the middle, right? And it's like sort of symmetric in that rotational kind of way, but I don't know about Loch Nessie there.
I had conjectured, well, I think I'm thinking fundamental group rather than mapping class group, but so I had been thinking about Loch Ness and the tripod as being very similar, because you sort of like, you go around one loop from each and then you go to the second one around each, et cetera. And so it seems like they should be similar. But your classification theorem makes me think that there's genus accumulating in 3 directions rather than 1. And so I'm going to guess that the top 2 are the same, because there's sort of the ladder that has
top.
Yeah, that has 2 directions, and then the plane you sort of said there's sort of 1 direction, and it's got an infinite amount of genus accumulating.
Yes.
So that's my guess there.
Yes. BK has got it. So this is exactly the way to think about it. Now, instead of trying to think, it's really hard if you try to think about making the surfaces look the same, which is usually what I try to do in the finite type case. I really try to like see if I can stretch and pull and make them look the same. Here, it's really better to think about the classification theorem and try to count how many ends do I have, how many of them are accumulated by genus, and use that instead. And so this is exactly what we can do here. So as BK said, our top 2 surfaces, we have 3 directions, 3 ends that we can kind of go out, and all of them have genus accumulating out towards them. And that's the same thing that's happening over on the top right. We have that ladder surface with our 2 ends accumulated by genus, and then our single waffle, which even though it looks like we have a lot of ways to go out, as we saw with when we were looking at the Euclidean plane, really there's just 1. And so then we can use that same intuition that we just built to see that that means that the bottom 2 surfaces are actually the same too. Because in both of these cases, we have a single end that's being accumulated by genus. And so it turns out that these are just 2 two surfaces that we have on this slide. Okay.
So we have a question. The real line can be compactified with a single point as well.
Yes. Like I said, I'm not giving you the actual definition of the ends because it involves like looking at like, you have to look at some like direct limit or whatever, inverse limit, I forget which way it goes, of like kind of subsurfaces that are kind of going out towards that end. And so it's a little bit technical. But yes, that is a good point.
Your metaphor of like what's left when you delete a ball centered somewhere definitely says two pieces for the reals.
Exactly. Yeah.
Okay.
Yeah. Okay. So one thing I noticed when I was going through my slides yesterday is that so far most of my surfaces have all had infinite amount of genus. They basically have had all the ends accumulated by genus. So like even this side, again, we have a picture of all of these things accumulated by genus. Here's another example. If you look at the blooming cantor tree, the one in the top left, where you can see that intuition of like, as you delete larger and larger compact sets, you are kind of getting more and more disconnected pieces on the outside. So that can kind of help you see how these two are different, because even though they both kind of are going out in many directions, with a waffle, you just get a single piece on the outside. Whereas here you actually, another way to think of this surface is like a sphere or like an infinite genus surface with a cantor set deleted. Or like, how can you think of it? You can think of a sphere with a cantor set deleted and then genus accumulated to every point in your cantor set. So they're very different like pictures, but really they're describing the same thing. So it's a little hard sometimes because I think, at least for me, my intuition from like the finite type setting doesn't always lead me in the right direction. Okay. So yeah, I want to just give two examples of things that don't have any genus. So we have our Loch Ness Monster, and we have a similar type of surface, which is called the flute surface, where instead of accumulating that one end by genus, I'm now going to accumulate it by isolated punctures running out. And the reason I drew it fluted is because if you think of putting like a hyperbolic metric on it, you somehow get like these cusps. And then the other one is taking our blooming cantor tree and just getting the regular cantor tree. So here, it's again, this is just a sphere now with a cantor set deleted. But you can kind of draw it in the same way. You have this kind of like infinite branching as you go out to these ends. Okay, so those are just some, so you can see there's a little bit more variability. It's just easy sometimes. There's only like 7 or 8 of all the infinite type surfaces which are named, and so people tend to focus on those ones a little bit because it's easier to say them. Okay, so for these infinite type surfaces, we still have a mapping class group. And it's defined in the exact same way. This is the group of orientation preserving homeomorphisms of your surface up to homotopy. But of course, things can be a lot more wild here. So for example, if we ask kind of our same collection of questions, immediately we don't get finite generation, right? Like the fundamental group is not even finitely generated. So like this is kind of out the window as a hope. But in fact, there are kind of nice ways that you can describe generating sets for at least some big mapping class groups. So for example, it's a theorem of Priya Patel and Nick Vlamis that if you look at the pure mapping class group, so this is now, I'm not going to let any of my ends get permuted around, then this is topologically generated by Dane twists and these maps called handle shifts, where you just kind of have like an infinite strip of handles and you move them kind of from one end to the other. So by topologically generated, it's not quite as good as getting generated. So you don't have that every element can be written in terms of these types of elements, but you get that every element can be written as a limit of elements written as these types of elements. So it's not as good, but in these kinds of really big uncountable groups now, it's kind of the best type of thing that you can hope for. So on the bottom, I have my picture of Priyam and Nick being awesome. Okay, so there are some good types of things that we can say, even though it's not as good as finite generation. Okay, so next question, we can ask about its center. So this was something that I a little bit brushed past in the first part of the talk, but we can go into a little bit more detail with here. And it turns out the answer is the same, and the proof is going to be essentially the same. So this is a result of myself and Justin Lanier, who's a graduate student here at Georgia Tech and is going to be starting an NSF postdoc at UChicago in the fall. And so we show that if S is an infinite type surface, then its mapping class group still has trivial center. And this is a picture of us eating ice cream, because if you are my collaborator and my friend, we will always eat ice cream together when we do math. So that's why I picked those pictures. But the key tool to show that this mapping class group has trivial center is using the Alexander method. So this is something that we have for finite type surfaces. And it's a way to tell whether or not your mapping class group is trivial based on this kind of very combinatorial condition, which is how it's acting on curves. So the statement is, if F is a non-trivial mapping class, so it's not homeomorphic, not homotopic to the identity, then there exists a curve C on your surface that is acted on non-trivially by F. So F of C is not equal to C. So this is really great because it gives you, again, like a very combinatorial way to check whether or not your mapping class is trivial. And so this is something that is a very well-used tool in the finite type set. It's used to show, in the finite type setting, to show the mapping class group has trivial center. It's used in the proof of like the Day-Nielsen-Beer theorem, and it's used everywhere. We use it a lot. And so luckily, we actually have this in the infinite type case. So this is a recent result of Jesus Hernandez, Israel Morales, and Fran Valdez from that paper that I showed some pictures from earlier. They extended this result to infinite type surfaces. And so with this in hand, it's actually really straightforward to show that the mapping class group is trivial center. So it's really, we just need 2 more tricks, and then we'll do the proof, which is going to be like 5 lines. So these are just 2 facts, which I'm going to ask you to take on faith. These are 2 facts about Dane twists. And the first one is very intuitively clear. At least one would hope for it to be true. And what it says is, if we have 2 curves on our surface, the corresponding Dane twist about them will be equal only if those curves are actually equal. So you're not going to twist about 2 different curves and get the same map unless you actually twisted about the same curve to start with. So that's good. That's kind of what you would want. And then the second I call like the conjugation trick. And it gives us a nice way to look at how a map acts on our Dane twist. So if we have some other mapping class F, and we act on our Dane twist about A by conjugation, then actually what we're doing, that would be the same as if we instead just twisted about the image of that curve under F. So this is a really nice way. The action by conjugation is really giving us a way to just get another Dane twist about a curve, which is just the image of the curve under that map. So if you want to know more about these types of really nifty tricks, you could look in, do I have it? You can look, and this is a shout out to my postdoc mentor, Dan Margley. This is a primer for mapping class groups. So this is the Bible of mapping class groups. It's by Benson Farb and Dan Margley, and it has lots of basically all the tools you need to study finite type surfaces through the lens of mapping class groups. Okay, so now with these 2 tricks in hand, this nice kind of identity relation and then this conjugation trick, we're ready to go ahead and prove that the center of any mapping class group, this works for both finite and infinite type surfaces now that we have the Alexander method in place in both settings, and it's really easy. So what are we going to do? We're going to assume that we have a non-trivial mapping class, and so then by the Alexander method, that means that there's some curve on our surface that is moved by F. So we have some curve C such that F of C is not equal to C. Awesome. So now what are we going to do? We're going to apply our conjugation trick. Our conjugation trick says, well, if we conjugate our Dane twist about C by F, then we get the Dane twist about F of C, right? So now we have this kind of equality. I guess I should have written equality. We have F of F TC F inverse equals TFC. So now we're going to do our contradiction. So let's assume that we had a non-trivial element in the center. So assume that F is central. So that means that F actually commutes with every other element in the mapping class group. So in particular, it commutes with our Dane twist about C. So what does that mean? It means that we can write F TC F inverse as just TC, right? We can move the F over to the other side and the F and the F inverse cancel, and we're just left with the Dane twist about C. But now we have 2 equalities that say that T of C is equal to TF of C. But we already know that that's not true because F is not trivial. And so by the Alexander method, F of C is not equal to C. And that's it. That's the whole proof. And that's the same proof that goes through in the finite type setting. Does anyone have any questions about that? I just like to give that proof because it's like very rare you can put a proof on one slide. So.
I have a question.
Okay.
So of the two things that the two preliminaries, the one that seems like it would take some proving is that if you have different curves, then the Dane twists about them are different mapping classes. Is that actually hard, or is there a trick?
No, neither of them are too hard. They're both in the primer and they're like a line or maybe a paragraph or something. They're pretty straightforward. Yeah, so it's not too much to do. Yeah.
There's been a lot of enthusiasm for this proof in the chat, but no concrete questions yet.
Okay, cool. So then we will move on because we have one more proof that I would like to show you. This is a proof by shortness, and the next is going to be a proof by picture. So let's see if we can get to that. So we're going to come back again to our list of questions about our mapping class group over the infinite type surface. And we're going to ask this same vague question, but now we kind of know what question I'm really asking. I'm really asking if we have this kind of subgroups alternative that I described before, this strong tits alternative. And the answer is, did I always say? I can't tell. And the answer is like no, as in it doesn't have the same subgroup alternative, at least, that we have in the finite type case. So in particular, this is another result joint with just and linear. And we say that, in fact, the mapping class group of an infinite type surface doesn't satisfy the strong tits alternative, right? So again, this alternative was saying that every subgroup is either virtually abelian, so it contains a finite index abelian subgroup, or it contains a free group, a non-abelian free group. And so the idea of proof is kind of straightforward, right? Well, all we have to do is provide for every mapping class group of an infinite type surface some subgroup that it itself is not virtually abelian and doesn't contain a non-abelian free group. So the idea of proof is straightforward. The only problem is actually there's a ton of different infinite type surfaces. So it seems like it might be a little tough to find a subgroup that can live in all of them. But it turns out there's a nice one. And it might not look nice at first glance. So this is called Z with Z. And it's on a Z's worth direct sum of Z's with an action of Z on it by conjugation. And this is a group that is not virtually abelian, and it does not contain a non-abelian free group. But it also looks like this. And I call myself a group theorist, but like I want to do the topology and geometry that gives me answers about my group. I don't actually want to like get into some nitty-gritty group theory things. Okay, so already this description of my group is not making me super happy. So I want to interpret it into something that is a little easier for me to understand. And the way I'm going to do that is by looking at a related group. So this is Z2 with Z. And this is kind of the same, except now we replace that infinite direct sum of Z2s, Z's, with an infinite direct sum of Z2s. And so the reason that this is an illustrative example is because it has a really nice description. So this group is often called the lamplighter group. And the reason it's called this is because you could think of your like infinite direct sum of Z2s as a row, an infinite row of lamps. And each of those lamps, right, it can be on or off. So that's my Z2, right? It can be on, it can be off, it can be on. And it can be on or off by my lamplighter, right? My lamplighter can walk along and it can turn a lamp off, it can turn a lamp on. And so that little person walking back and forth lighting our lamps, that's our Z action. And so this picture gives kind of a very concrete picture to what that somewhat abstract description of my group was. So yeah, this is my lamplighter group. And so I want to now interpret my Z with Z into the same picture. And the way I'm going to do that is by replacing my Z2 lamps with Z lamps. So now, instead of walking along and turning my lamps on and turning my lamps off, I'm going to walk along and I can turn my lamp to 1,000,000, or I can turn my lamp to -5, or I can turn my lamp to 20, or whatever. And so this is kind of now a pictorial type of representation for this somewhat complicated type of group. And so now that I hope you will believe me that this is my right picture for my group, instead of needing to find that kind of complicated description of my group in each of my mapping class groups, I just need to find this picture in my group. And really, when I say that picture in my group, it means I need to find a picture like this on my surface. And so that's what I'm going to try to do. So the first step in that is, yeah, so that's, I just said that, right? I just want to show that there's a Z with Z as a subgroup of every mapping class group. So the first step in doing that is I want to find a way to kind of divvy up my infinite type surfaces into different bins. And the bins I'm going to use are these three. So this is a takeaway from the classification theorem. This is not obvious, but this is something that you can get from it. And it's that every infinite type surface falls into one of the following categories. We either get an infinite pool of genus, or a countable collection of isolated punctures, or a Cantor set of punctures, with the caveat where that Cantor set is like a clean Cantor set. We don't have any of those punctures accumulated by isolated points. So these are now, this is my chunking that I'm going to do of my infinite type surfaces. And now all I have to do is produce that little lamplighter picture for each of these kind of three types of surfaces. Okay. So first we have the case where we have infinite genus. So here again, what do I want? I want a Z's worth of Z's, and I want a lamplighter to move around and light my Z's up to whatever number I want them to be. And so here, I kind of mentioned this a little bit when I talked about the generating set for the pure mapping class group. We have this thing called a handle shift, where we're just shifting these handles from one end. Instead of shifting it from one end to the other, we're just going to shift it from one end back to that end itself. So that's my map H. It's just this handle shift. It shifts each one over by one click. And so that's my lamplighter. My lamplighter moves around from each of my handles. And then my Z is my Dane twist about alpha. Right, so this is where it's handy that alpha is an infinite order, like the Dane twist about alpha is an infinite order mapping class. So we get a whole copy of Z there. And so this is my picture. Each of these handles gives me a copy of Z, and my lamplighter can go along. Really here, the lamplighter is not so much going along as it's shifting everything to the middle, and then I can choose what Z I want and then shift it back. So here's for my infinite genus, this is my Z with Z. And then I'm basically going to draw the same picture now when I have I have countably many isolated punctures. So here I'm going to do the same thing. Now instead of taking a strip of handles, I'm going to take a strip of my isolated punctures. And the only difference here is that I need to take a curve now that's bounding 2 punctures. The reason I want to take a curve bounding 2 punctures is that if it was just bounding 1 puncture, I could just homotope it into that puncture. And really a Dane twist about that would be trivial, because it would be the same as just fixing that puncture. So I want to take it around 2 so that we get a non-trivial Dane twist. And then I have the same thing. The only little difference I have here is instead of taking just my single shift, I'll take my shift squared, because I want to make sure that I move that curve completely off itself so that I don't get any interactions between my copies of Z. So this is my second Z with Z. And then finally, you folks could probably draw this picture for me. We have the same thing now when we have a Cantor set. So the one nifty thing about a Cantor set is they're self-similar. And so a Cantor set has lots of Cantor sets in it. And so what I'm going to do is I'm going to break my Cantor set up into a Z's worth of Cantor sets, and I'm going to line those up on a strip going from one end to itself. And so now my handle shift / puncture shift is now a Cantor shift, and I'm going to be shifting these disks containing my Cantor sets. And here you can either do, in my picture I drew like you could do a pseudo-Naza there, but actually you could just take the curve bounding that disk like I did before for the punctures and just twist around that. And so these are going to be, again, this is my ZVC. And so that's
If you'd like to unmute and clap, that would be great. It's not a question, but my favorite idea from the chat is that we replace the Erdős number with the loving ice cream number. Yes. and that it requires photographic evidence.
That's now my mark is whether I've made as a mathematician, is if I have a loving ice cream number.
Yes. Well, and I have one question just to make sure I was actually understanding. So all of this is sort of intrinsic to the surfaces. So like you can't tell the difference between a Mobius strip with 1 half twist or 3 half twists from this perspective, because that's about how it's embedded in space, not how it's connected as a surface. Yeah. Okay.
Well, luckily for me, I can't tell the difference. I can't tell the difference between any Mobius strips because I have no Mobius strips. Yeah. So, but yeah.
I don't have a question. I just want to share that my Loch Ness Monster plushie really enjoyed this talk.
Nice. I'm so I can scroll. Can I see again? Oh, that's adorable. Nice.
That's a small one. That's not one of the infinite ones, right, Lauren?
It's not infinite.
I was trying to count there, but it's too fast.
It's hard to get a hold of them in real life, you know. They're very elusive.
Expensive.
Like the Loch Ness Monster itself.
Other questions from people?
I have a question. So, like, is it known, like, how, like, the failure of the big mapping class group to have the TITS alternative?
Yeah. So one of the.
Pointed out,
sorry.
Oh yeah. So you pointed out one example. I'm just wondering, there may be more type of example, or like, maybe that's the only type of example.
So we show that for all big mapping class groups, like, right, that division I did of the types of spaces of ends you can have means that we actually embed a ZVC into every single big mapping class group. But one of the questions that we asked in our paper is, for example, could you have some other type of TITS alternative? So the classical mapping class group like satisfies the strong TITS alternative, but there's also just the normal TITS alternative, or the classical TITS alternative. And this asks if you have, for every subgroup, are you either virtually solvable or you contain a non-abelian free group. And so that was a question that we gave examples where you can't actually have the classical TITS alternative, but we thought maybe there'd be some kind of dichotomy. Sometimes you do, sometimes you don't. It depends on the topology of your surface. But actually, we've been in correspondence with Daniel Alcock, who's a professor at University of Texas, Austin. And he has a proof that it actually you never do. So he builds a sort of like Grigorchuk group type thing construction that, so it basically embeds a quotient of a Grigorchuk group into every big mapping class group. And so that actually shows that no big mapping class group satisfies the classical TITS alternative. So maybe there's hope for some other type of subgroup alternative. That's not off the table, but any sort of TITS alternative at this point is kind of, yeah, not really available.
Can I add to that?
Oh yeah, Anshul. That's Anshul,
Anshul.
right? Anshul. I read
Yeah,
your paper
sorry.
about the loop graph
Cool.
a few weeks ago.
Cool. Yes, thank you. So there's also the question or the issue of since these big mapping class groups have some interesting topology to them, a sequence of mapping classes converges to a mapping class, that you might want the idea of virtual comes from the world of finitely generated groups, and it's possible that you want some more permissive version of that. So you might, for instance, ask that the quotient be coarsely bounded or something like that.
Yeah.
And to my knowledge, that's where you might more expect to see an extension of results of that kind from the small mapping class group setting.
Yes, I totally agree. Yeah. We talked about this a little bit. There was like an AIM workshop for the infinite type surfaces, and we talked a little bit with Mladen. And yeah, it definitely, that certainly virtual is not the right type of property to be thinking about for these really big groups. And so yeah, totally, you have to start thinking a little bit differently. Think about Polish groups. So yeah.
So from the title of this talk, big surfaces, I really wanted the square of the long line to be a big surface. But I'm guessing that's not even technically a surface. It's locally Euclidean. But by the what's the part of the definition of a surface would keep that from being a surface?
I don't know what that is.
It's not
The
second
long
countable.
line is you take the first uncountable ordinal and you stick intervals between them.
It's not second countable.
So second countable is part of the definition.
Yes.
Yeah.
Yeah.
Cool. I figured it was something like that, countable chain condition or something. Cool.
And if there's, for people who like to find silly counterexamples, Hausdorff is also normally assumed to be part of the definition of manifold.
Yes.
And therefore,
Yes.
So for the long line, or it's square, right? I mean, so the thing about the long line is there's no continuous functions to R that aren't eventually constant.
Yep.
So that means that's going to be a problem with defining what you mean by end.
gonna be a lot of problems if you take off second countable and like awesome. I feel like all of our notions of topology are gonna start falling apart. So yeah, at least for me, my ideas of a topology will start falling apart.
So Marissa, that's sort of interesting. I love the talk, and I'm definitely an algebraist at heart, and so you were really pulling on that, and then we got to the group, the worst group on the slides, and you were like, I got to be a topologist now. Like, so how do you identify along those lines?
I honestly, I'm a geometric topologist. And I'm a group theorist by upbringing. So like I did my PhD at UIUC, and so like Ilya Kapovich and like Igor Minev, like very much like more group, especially Igor Minev is very like combinatorial group theory, and that's who I took a lot of my like topology and like geometric group theory classes from. And so I always say like by upbringing, I'm a geometric group theorist, but honestly, I'm not. And it's a little bit misleading to call myself a group theorist. Because really, if it doesn't involve the topology of my surface or something, I'm out. I can't say anything. I really only want to do things that involve like constructions of curves on surfaces. That's my whole toolkit. So, yeah.
So, what is the curve complex for like a big surface? I mean,
it is trivial. That has diameter 2. Oh, okay. So because you can always just take something far away that's disjoint. And so the typical curve complex, if people aren't familiar, is you take an isotopy class of curves as a vertex, and you put an edge between them if they're disjoint. And so for the mapping class group of a finite type surface, this encodes a lot of like coarse geometry. So for example, the automorphism group of the curve complex is actually isomorphic to the extended mapping class group. But in the big sense, you still have this kind of Ivanov type rigidity, but somehow your graph that you're looking at is just trivial. And so there's other types of complex of curves where you can act with unbounded orbits, but not always. So in fact, for some infinite type surfaces, there's no action on any type of complex of curves where you have like an infinite diameter orbit. And so Anshul mentioned this a little bit, this idea of coarse boundedness, which has recently been introduced for these big mapping class groups by Kaz Rawafi and Katie Mann. And so this gives you some way of studying the coarse geometry for these big mapping class groups, which kind of the tools that we have in the finite type case are kind of break apart when you get to these ones. In fact, Anshul also has a paper about loop graph, I guess. So also some sort of like curve complex for the action of a big mapping class group.
I think we have time for maybe one more question. Any of our friends want, especially somebody who's new, have a last question for us?
I had a question going back to the classical Tits alternative. So for finite type mapping class groups, isn't the classical Tits alternative equivalent to the strong one because virtually solvable subgroups are virtually abelian? Do you know if like that's also true for big mapping class groups like this Berman, Lobatsky, McCarthy?
Oh, I don't know. I did not think of that. Yeah, I'm not sure.
Well, maybe that's our new project because we've been looking for one.
Yeah, let's do it.
You guys have to get ice cream together, and we need photos of you.
Oh, we've got
and
to ice cream together.
Yeah.
Oh, perfect. Yes. Can everyone join me one more time in thanking Marissa? This was lovely. Thank you.
Thank you, everyone, so much for coming. This was very, very nice.
So next Thursday, we have Andrew Cooper from the University of Pennsylvania, who's going to talk about point curve configurations in the art of war. Andrew, are you still here? Do you want to give us a sales pitch?
Yeah, so imagine juggling, but with tanks. And, a smattering
that seems like a really bad idea.
Yeah, a lot of things with tanks are a really bad idea.
I was thinking juggling. I'm not that good. Oh. The tanks are fine.
How do you feel about the peek-a-boom tactic for tanks?
I don't know this.
Oh, so my cadets actually just gave a presentation on ranking tanks today, and they were talking about their different like just based on their size and how far they were off the ground and whether they had more shielding up front or like all these other things. But like I guess there's this tactic where for NATO tanks they tend to stay low to the ground.
Oh,
and
behind the military crest of the hill. Yeah.
Yeah, and then pop up and it's peekaboo.
Yeah,
So,
No, I know this tactic. And I actually don't know anything about tanks. So the talk is going to be basically the idea with tanks, just like with juggling balls, is you don't want them to be in the same place at the same time. So if you are interested in questions like, how does a descent into war happen? What you care about is something, can be sort of modeled if you're juggling and your balls are about to crash into each other. And so we take the mathematics of point configurations and sprinkle a little bit of, pretty classical economics in it and some other stuff. Mostly I'm going to talk about the fact that you can reduce these things to combinatorial questions about simplicial complex, because, some tanks are allowed to be together. Like the US tanks and German tanks are allowed to be in the same place at the same time. That's not a bad thing. So there's a little bit of combinatorics involved, and yeah, it goes from there.
Cool. Looking forward to it.
I think we have to stop our recording, but one more time, thanks everybody.
Thanks everybody. We'll see you next Thursday.